Hi there! Today we will begin our journey into the world of digital electronics by examining 5 different logic ports: the AND, the OR, the NOT, the NAND, and the NOR. We will see how we can build such ports just by using transistors and resistors, and then we will see how they look like and how we use them in their integrated circuit form. All of this while learning a thing or two about Boolean algebra, which we will see it differs from the regular algebra even if applied to binary numbers. You want to see how? Let's begin!
Hi there! I am Carlo Carrano and this is Electronics Engineering Made Easy.
Let's start with the simplest logic port of all, the NOT gate. Here is the symbol, where A is the input and U is the output. This little circle over here is the actual symbol for the NOR operator. The rest of the symbol represents just an active component, an amplifier in particular. And in fact, the NOT gate is made of a simple transistor polarized in such a way that it works in only 2 possible states: off or open, where it does not conduct any current, and on or closed, where it does conduct enough current to be in saturation. To obtain this behavior, we just need a couple of resistors, one on the collector to limit the maximum amount of current, and one on the base to limit the current that goes through the base emitter junction when the base is positively polarized. And so this is the whole schematic of a NOT gate. Let's now figure out how it works. If we put a positive voltage in A, basically the plus VCC, the transistor will be on and a current will flow between collector and emitter, limited only by the resistor on the collector. Because of that, the output U will be at the ground level. If we connect A to ground instead, the transistor will be off or open, and there will be no current flowing through it. As a result, U will find itself at the positive voltage plus VCC. Now, if you recall the previous episode, we said that we associated the plus VCC to true, or to the number 1, and we associated the ground level to false, or the number 0. With such information, we can build what is called a truth table, which is a table that represents how a logic circuit works, in this case the NOT gate. To build this table, we list all the input symbols on the left side, then we list all the output symbols on the right side, and we draw a cross to divide the inputs from the outputs and the names from the rest of the table. In this case, we have only one input A and one output U. Once that is done, we write on the left side of the table all possible combinations of ones and zeros on the inputs. In this case, since there is only one input, we will have only a 1 and a 0. Then, on the right side, we write the output values corresponding to the inputs on the same line. Again, in this case, there will be only a 1 and a 0. This table now tells that every time the input is at 0, the output is at 1, and vice versa, every time the input is at 1, the output is at 0. This logic function, therefore, does just one simple thing. It generates an output that equals the inverse of the input, and for this reason the NOT gate is also called inverter. Using the Boolean algebra, which we mentioned in the previous video, we can define for each basic logic function a specific symbol. For the NOT, or inverter, the symbol is simply a dash on top of the name of the input or output. And so, using the Boolean algebra notation, we can write that U equals the inverse of A, or U equals not A. This notation doesn't seem to be important right now, but you'll see later how important it becomes when we need to design logic circuits. Let's now move to the lab and run some experiment to see how practically a NOT gate works. Here is a printed version of the circuit we just talked about. This is, of course, a real-world circuit with real components values. The transistor can be any NPN with a beta of at least 200. The choice is yours. And that's why I didn't mention the type. However, if you really want to know, I'm using a BC547. The resistor on the base is of 4.7K, and the resistor on the collector is of 330 ohms. I calculated these resistors based on a power supply of 5 volts to mimic the TTL circuits. If you plan to use a different voltage, these values will have to be adjusted, of course. Here is the circuit mounted on a breadboard. Here is the transistor. This is the resistor on the collector, connected to the plus 5 volts on its other end. This other one is the resistor on the base side, which goes to this cable, used as an input, which is currently connected to ground, or the logic 0. If I move it to the positive, then the input will change to the logic 1. The transistor emitter is connected to ground, and on this test point, which is connected to the collector, we can read the output value. So let's power it up, and let's see how it works. Right now the input is at 0. Now let's take the logic probe and let's see what is on the output. And since the red LED is the one that turns on, the output is a 1. Now I'm going to set the input to 1, and I'm going to check again the output with the probe. This time it is the green LED that lights up, which means we have a 0. Let's write down on the paper the truth table we just obtained with the experiment. We have the single input A and the output U. 0 and 1 are the possible inputs. With the input 0 we just read an output of 1, and with the input of 1 we read a 0. And this confirms the behavior of a NOT gate. Let's now take a look at another way of making a NOT gate, and that is this IC. But this IC contains not just 1, but 6 ports in it. Look at the difference in sizing of this IC with 6 ports and a single port made out of discrete components. Let's now put the IC on the breadboard, and let's take a look at the contents of the IC, or what is called the logic diagram of it. Here is what the inside of this IC looks like logically. There are 6 inverters in it, or NOT gates, of course. The power supply for all of them is applied to pin 14, the plus VCC, and to pin 7, the ground. We will now take a closer look at the first of these ports, which uses pin 1 as the input and pin 2 as the output. The other ports work basically the same, they are just connected to different pins. So let's complete the circuit. Pin 14 goes to the positive of the power supply, and then pin 7 goes to the ground. Now pin 1 is our input, which right now I'm connecting to ground, or the logic 0. Pin 2 will provide us the output. I'm connecting another wire to it to easily touch it with the probe. The input of the gate is connected to 0 right now. If I now touch the output with the probe, the red LED shows up, which is the 1. If I now connect the input to the plus 5 volts, which is the logic 1, the output should go to 0. And yes, that's exactly what happens. You see, this IC is very easy to use because it doesn't need any external component, no resistors and no transistors. Let's now move back to the drawing board to talk about the next type of port. Let's start by drawing a resistor connected to the positive of the power supply. Then we add a transistor and another resistor that makes up the input A. And now, instead of connecting the emitter to ground, we connect it to the collector of a second transistor, and it will be the emitter of this second transistor that is connected to ground. And now another resistor, this time on the base of the second transistor, that makes up a second input, which we call D. And finally we take our output U on the collector of the first transistor. Let's figure out how this circuit works, and let's start from the truth table. This time we are going to have 2 inputs, A and B, and one output U. Let's now write down all the possible combinations of inputs, 0, 0, 0, 1, 1, 0, and 1, 1. Now, a 0 on both inputs means that both transistor bases are connected to ground. The 2 transistors are therefore open, they do not conduct any current, and therefore the output will be at the plus VCC level or a logic 1, with which we can update the truth table. A 0 on A and a 1 on B causes the first transistor to remain open while the other transistor will start conducting, so it is going to behave like a closed switch. However, no current can flow through the resistor on the collector of the first transistor because the first transistor prevents the current from flowing. And therefore the output will not change, we will still have a 1. A 1 on A and a 0 on B will make the transistors work respectively as closed and open, but still there will be no current, and so again the output stays to 1. Finally, putting 1 on both inputs makes both transistors closed or on, so now the current will flow and the output will be brought down to the ground level, which is a 0. So here is the complete truth table. If you notice, it looks like the two inputs are multiplied together, and the output is the inverse of the result of the multiplication, for which you see also the Boolean representation. We represent this behavior with this symbol. The little circle here on the front tells us that there is a NOT operation involved, and that operation is in front of another operator which we call AND. The two together make what is called a NAND gate. Let's go check in lab if it really behaves like we thought. And here we have again a printed version of the circuit just examined. This one has two transistors with a beta of 200 or more, one collector resistor, a gain of 330 ohms like before, and two resistors on the basis to create the two inputs A and B, each one of 4.7K like before. Here is the test circuit I made based on this circuit. You can see the two transistors here, where the emitter of the first one is connected directly to the collector of the second one. The emitter of the second transistor goes to ground, while the collector of the first transistor goes to the positive of the power supply through the 330 ohms resistor. Here are the two resistors connected to the base of both transistors, 4.7K each, which make up the two inputs A and B, which right now are both connected to 0, the ground, through these two wires. This pin represents the output taken directly from the first connector. Let's power the circuit and let's see how it works. Let's also prepare the truth table, the two inputs A and B, and the output U. And here are the four possible combinations of inputs. Right now, the inputs are both at 0. Let's measure the output. And the output is a 1. Let's write it down on the truth table, and now let's change the inputs, with a 0 on A and a 1 on B. Let's measure the output again. And it is still a 1. Now let's switch both inputs. Now A will be at 1 and B will be at 0. And the output is still at 1. And finally, let's put both inputs to 1. And the output now is 0. And so we have proven that our previous estimate on the board was correct. Like with the NOT gate, also the NAND gate can be found as an integrated circuit. However, because of the available number of pins, the number of ports in the IC is limited to 4, as you can see from this diagram. Again, we can power this IC with the ground on pin 7 and the plus VCC on pin 14. And this is the actual chip, an SN7400. Let's put it on the board so we can test it too. And let's temporarily disconnect the power supply and make the connections on the chip. So, pin 14 goes to plus VCC, and pin 7 goes to ground. I'm going to take now these two wires and use them as the inputs for this new circuit. I'm going to use the first port of the IC, which has the inputs on pin 1 and 2, which right now I am connecting to ground. The output instead is on pin 3, which I will provide right here with this other wire. Let's now power up the circuit and read the output when the two inputs are at 0. And the output is at 1, which is exactly what we found with the discrete circuit. Let's now move input B to 1, while A is still at 0. And the output is still a 1, like the table suggests. Let's now switch the two inputs. A becomes 1 and B becomes 0. And the output is still a 1. Finally, let's connect both inputs to 1. And the output now is a 0, as we expected from the previous truth table. Let's now go back to the drawing board, where I will show you how to make an AND gate. You will soon see that the AND gate is more complicated to make than the NAND. And in fact, because the technology uses transistors, which are basically inverting amplifiers, it is easier to build ports with a NOT than ports without. To make an AND gate, we have to start from a NAND one. Here is the collector resistors, the two transistors in series, and the two inputs A and B. The output of this NAND goes to a NOT circuit obtained with another transistor and two more resistors. It is the combination of these two elements that makes the AND port. The NOT at the end negates the NOT that is part of the NAND circuit, and so it becomes an AND gate. And here is the representation for logic circuit schematics. You can see that it is the same as the NAND gate, but without the NOT at the end that makes it an AND. Let's go to the truth table now. Here are the possible combinations of inputs. With two zeros at the inputs, the output of the NAND section will be a 1. And since that is the input of the NOT gate, the final output will be a 0. With 0 on A and 1 on B, the NAND output will be a 1, and the final output a 0. Similarly, with 1 on A and 0 on B, the NAND output will still be a 1, and therefore the final output will be a 0. And finally, with both inputs at 1, the intermediate output will be a 0, and the actual output a 1. Using Boolean algebra, we can now write U equals A dot B, or equals AB. No NOT symbol on top. And this is the circuit printed on paper with actual components. Again, we have this left section with its two transistors, the two resistors on the basis and the resistor on the collector, which act as an AND port. On the right side, we have an inverter circuit, which its input is fed by the NAND output, and so it negates the NOT on the NAND. The output of the circuit will work therefore as an AND function. Let's now write the truth table for this circuit with two inputs A and B and one output U, and let's write all the possible combinations of inputs. Here is the actual circuit. On the right, you can see basically the same circuit we built as an AND circuit, but its output goes now to the input of the NOT circuit built on the left side. This pin will allow us to read the output. So let's now power up the circuit. These two wires are the inputs of the circuit, and currently they are both connected to ground, giving to each of the two inputs a logic 0. Let's now read the output, and it is a 0. Let's now put the input B to 1, and the output is a 0 again. Now we switch the input A and B's, setting A to 1 and B to 0. And the output is still a 0. And finally we set both inputs to 1. And the output this time is a 1. And so we have confirmed again that this circuit corresponds to the AND function. And again, we can use an integrated circuit to make the AND ports. And this is how the IC I decided to use looks like. Once again, pins 14 and 7 are used to power up the module, and the pin out is practically the same as the IC with the NAND gates, but this time these are AND gates. It is a through-the-hole dual-inline configuration with a total of 14 pins. This little IC covers 4 circuits identical to the one currently assembled on the breadboard. Let's now put the IC on the breadboard and let's connect the power to pin 7 and 14. Pins 1 and 2 are used for the inputs of the first port in the IC, which for now we connect to ground, which is the logic 0. The output of the second port is on pin 3, and we connect to it this other wire to easily make the reads with the logic probe. Let's power up the circuit now. The inputs are both set to 0, and the output is also 0, as expected from the earlier discussion. Now we connect B to 1, while A is still 0, and we make another read, and the output is still a 0. Switching the two inputs gives us again a readout of 0, And finally, connecting both inputs to 1, we finally read a 1. And so we have again proved that the circuit works as we expected. Let's now examine another kind of port. With an AND gate, we connected two transistors in series. Let's see now what happens when we connect them in parallel. And so we have the first transistor with its two resistors, then we add another transistor, but we connect its collector directly to the one on the first transistor, and then this second transistor has its own input. The output is taken on the two collectors. Let's extract the truth table for this configuration and let's see where it will bring us. With a 0 on both A and B, both transistors will be off and therefore will not draw current from the resistor at the collectors. The result is that the voltage at the two ends of the resistor is the same, which means that the voltage at the collectors is plus VCC, or a logical 1. Putting now a 0 on A and a 1 on B, the transistor on the left will be off or open, while the transistor on the right is on, so it will behave like a closed switch. The transistor will then drain current from the resistor on top, causing the output to go low, which is the logic 0. Putting a 1 on A and a 0 on B will sort a similar effect, but now the transistor on is the one on the left, and the transistor off is the one on the right. So this time the current will flow through the transistors on the left, and the output will still be a 0. Finally, a 1 on both inputs causes both transistors to be on, and therefore the output U will once again provide a 0. The behavior presented by this circuit is called NOR function, and the device is a NOR gate, which has this representation made with 3 arcs, and a circle represents the NOT. In Boolean algebra, we represent this function as U equals NOT A plus B. Yes, it looks like the inverse of the addition, but note that in Boolean algebra the value of 1 plus 1 is still a 1. And this is something important to remember. We are talking about logic operations here, not arithmetic operations. If one thing is true and another one is also true, if we put them together, we still have true. The numbers 0 and 1 are used for convenience, but remember they don't represent actual numbers, just logical states. And once again, here is our circuit printed on paper with actual component values. 2 transistors, the emitters are connected together and to the ground, the collectors are connected together and to the positive of the power supply through the now usual 330 ohms resistor. And finally 2 resistors on the 2 bases that constitute the 2 inputs of this logic gate. The output is taken on the collectors. Here is the circuit mounted on a breadboard. Here are the 2 transistors. They are mounted against each other so that the 2 collectors can be directly connected to each other. The 2 emitters are both connected to ground. The collectors together go to the positive through this resistor of 330 ohms, and we have also a pin there to be able to read the output with our homemade probe. And last but not least, the 2 resistors on the 2 bases that make the 2 inputs of the port. The inputs are also connected to ground, the logical 0, through these 2 white wires. Here is the truth table that we will be using to figure out how the circuit works. So right now, both inputs are set to 0. Let's power up the circuit and let's read the output, which is a 1. Let's now set the input B to 1 while input A remains to 0. And the reading is still 0. Now let's set A to 1 and B to 0. And the reading is a 0 again. And finally, let's set both inputs to 1, and the reading this time is 0. And so this truth table reflects exactly the one that we determined by examining the circuit, which tells us that this is actually the implementation of a NOR port. Here is the pinout of an IC that provides 4 of these NOR ports, an SN742. Of course, it works like the ones we have already examined. Power supply is on pins 14 and 7, and there are 4 gates available, just because there are no more pins available. This time, pin 1 is the output, and pin 2 and 3 are the inputs for the first port, and all the other 3 ports are connected signally to the pins. And here is the actual chip. However, this time I'm not going to bother you any longer by assembling a circuit with it to take more readings. I will leave instead this exercise entirely to you. Instead, let's now make the OR port, the last for this video. Similarly to what we did with the AND gate, we will make first a NOR port, and then we will attach at its output a NOT gate. Here, like this. Let's draw the truth table and a list of the possible inputs. Again, when A and B are both 0, we will have a 1 on the NOR part, and the NOT will convert it to a 0, and similarly for all the other cases. And so, this time we have a 0 only when both inputs are at 0. We will have a 1 in all other cases, the OR gate. So, to make it more visible to you, here is also the line that separates the NOR part from the NOT part. And here is the symbol of the gate, which is the same as the NOR gate, but without the circle representing the NOT at its output. And finally, the Boolean representation of the OR function, U equals A plus B. Don't forget, this is a logical expression, not an arithmetic one. Therefore, 1 plus 1 equals still to 1. This is the circuit with all the component values. This is its implementation. This side is the NOR and this side is the NOT, and together they make an OR. Let's now verify with the truth table. With 0 on both inputs, we have an output of 0. With 0 on A and 1 on B, we have an output of 1. Switching the inputs, 1 on A and 0 on B, we still have an output of 1. And finally, putting both inputs to 1, we have again an output of 1. Here is an example of IC containing 4 OR gates. This is an SN74LS32. Again, pin 14 and 7 connect the IC to the power supply, and you can see how the inputs of the first port are on pins 1 and 2, while the output is on pin 3, and similarly for the other ports. And this is the actual IC. And since we now know how to test the IC, I will let you do that on your own time as an exercise. So, today we have seen 5 different logic gates or ports, the NOT, the NAND, the AND, the NOR, and the OR. We have also seen how it is easier to build inverting gates because of the way transistors actually work. And we have seen that obtaining in practice non-inverting ports requires more components, and so we reach the paradox where simpler logic ports have more complex implementations. Now that we have the basis, next time we will start looking at something more complex, obtained as a combination of 2 or more ports of the kind we have seen today. It is actually interesting to notice that if you have only NAND ports or only NOR ports, you can create any other kind of logic port. You don't believe it? Well, keep following the series and you'll see how to do that. See you in the next video, and as usual, happy experiments!